So I eyeballed a lot of the homework, but I graded question 10 in detail. And by and large, so some people didn't get that far, but those who did, by and large, looked like they were doing the right things, had the right steps down and stuff. Some logistical details here and there. So let's, I don't have my paper, so I got to redo the problem again. Okay, so here's the circuit we're trying to analyze. You got to write down equations, okay? Maybe every time that you filled in a value for Z1 in your truth table, you reanalyze the circuit in your head, or maybe you wrote the equations down on a piece of scratch paper. Put it all in your homework, okay? Because it's really easy to make mistakes filling in the truth table, right? But if you've got the right equation down, I know that you analyzed the circuit correctly, and you know, somewhere in the 500 ones and zeros you were trying to calculate, you made a mistake or two. That's not a big deal, okay? But make sure you show the equations. So what things do we need equations for in here? What are the inputs to this circuit?
X.
X, is that the only input?
And the clock.
And the clock, we don't usually call that an input. It technically is going in, but it's not going to show up in any of our equations. So it's really one input X. What are the outputs?
Z1, Z2.
Z1, Z2, two outputs. Okay. So what is there to calculate in here? Obviously Z1, Z2 because they're outputs. What else?
T0.
T0 and T1, right? The inputs to the flip-flops. We're not going to calculate Q0, Q1 bar, right? Those are outputs from flip-flops. If we know the input to the flip-flop, that'll tell us what Q0, Q0 bar are, and so on. So we're not going to write equations for those. We're going to derive those from T0, T1. So start your state diagram. So here's X. And my suggestion was to make a state assignment table, which the majority of people skipped. You don't really need to do this if you know exactly why you're doing what you're doing, but this will help you keep track of why am I writing 0, 1 here? Is this the name of a state? Is it the value of the inputs? Is it the value of the y's, right? So 2 flip-flops, 4 possible states. Let's go ahead and name them. So Q1, and you can work with Q, you can work with Y. I tend to work with Q's, but the Y's are the same as the Q's, so either way is fine. So I'm just going to name this S00, S01, S10, S11. And so I'm going to have present state. Put my table right in the middle of the action. All right, so I want to list the combinations of Q1, Q0 for each possible input value. So here I'm going to add my present state values, Q1, Q0. So those are kind of like the input side of our truth table, right? 0, 0, 0, 0, 0, 1, our usual 8 rows for all the combinations of those 3 variables. And our goal is to figure out what the next state is, which means we need to figure out the new value of Q1 and Q0. And the only reasonable way to do that is to figure out the values for T1, T0, and then use our knowledge of T flip-flops to write in what the outputs do. So we need to write values for T1, T0. So this is where equations come in. So let me scribble some equations down here. T1 is not too bad. T1 is an OR gate. One input is X. The other input is Q0. So T1 is XOR Q0. T0 is a little monstrous. T0 is an XOR gate, and one input is Q0. So I'm going to write T0 equals Q0 XOR, and the other input comes out of an OR gate. So it's an OR of Q0 bar and what's the other input to the OR gate? Well, it's the output of this 3-input AND gate, but it's also Z1. So I'm actually going to go ahead and write Z1 here, because I'm only doing this so I can fill in my truth table. And if I calculate Z1 first, then I can just OR that with Q0 bar, XOR with Q0. And then we'll fill in the last values. The outputs usually just kind of like hang around on the side. They don't usually come into play in a whole lot. So Z1 is an AND of X, Q0, and Q1. And Z2 is the inverse of Q1. So it's just Q1 bar. So there's my equations. Well, I'm not too worried about my outputs. I may as well just put them in right here, and I know I'm going to use Z1 in a moment anyway to find T0. So let me put in some columns, Z2, Z1. I don't have to label these outputs, but I'm going to just put a label there anyway. So Z2 is just the complement of Q1. So I'm just going to go down Q1, and I'm going to toggle it. All right, that's Z2. Z1 is an AND of X, Q0, Q1. Well, X, Q0, Q1 is a 1 in this last row, and at least one of those is going to be 0 everywhere else. So the AND is going to be a 0 in most cases. All right, T1 is the OR of X with Q0, so this first and third column get ORed together. So that's a 0, 0 and 1 is 1, 0, 0 is 0, 0 and 1 is 1. And these last four rows, X is 1, so the OR of X with Q0 is always going to be 1. So these are all 1s. And then T0 well, you can do this by hand, but I'd actually like to simplify this a little. I mean, I can start off Q0 is a 0. Okay, so if Q0 is a 0, Q0 bar is a 1, and 1 ORed with anything is going to be a 1. So if Q0 is a 0, this is going to be 0, X ORed with 1, this is going to be a 1. So I know this is a 1 everywhere that Q0 is a 0. On the other hand, if Q0 is a 1, this is 1 X ORed with something. For that X OR to be true, this something has to be false. We need 1 X ORed with 0. Well, if Q0 is 1, Q0 bar is 0, so that's 0 ORed with something. So this thing in parentheses is just Z1. So if Q0 is 1, we need Z1 to be 0. So Q0 is 1, we need Z1 to be a 0. Well, that happens here. And Q0 is 1, we need Z1 to be a 0. That happens here. Q0 is 1, we need Z1 to be a 0. That happens here. Q1 is 1, we need Z1 to be a 0. That does not happen, so that's a 0. So about half the people had T0 wrong, but their truth tables agreed. So I'm thinking there's something that I misspoke on or got misinterpreted about either XORs or something, because I saw the same equation for everybody, but there were a lot of zeros up here. So is there any question about how to do these XORs? And you can always do this. Right, so an XOR is exactly like an OR except for this last row, where if both things are 1, the XOR fails. So go back and try to redo this yourself. You can also simplify this by the analysis we just did. If Q0 is 1, if Q0 is 0, this is going to be a 1. So this is always going to be true. So T0 is true if Q0 is true. Or if Q0 is false, this is going to be, if Q0 is, I'm talking too fast. If that's a 0, this is going to be 0 XORed with 1. So if Q0 is false, that's always going to be true. If Q0 is true, this is going to be a 1. This is going to be a 0. Z1 has to be false. So if Q1 is true, or Q0 is true, Z1's got to be false. And if Q0 is false, this whole expression is true also. So this is actually just Q0 bar or Z1 bar. And we can De Morgan that. And it's just a NAND of Q0, Z1. So that gets you there also. All right, so we know the toggle flip-flop inputs. So what does the toggle flip-flop do? If T is 1, the output flips. If T is 0, the output stays the same. Right, so jot down your T flip-flop table. All right, well, let's just look at T1 and let's write the next state, Q1 plus. So we're only looking at this and this. And so if T1 is 0, we're just going to copy Q1 to Q1 plus. So this is a 0, this is a 1, and then T1 is 1 everywhere else. If T1 is a 1, we're going to toggle the current value of Q. So all these other cases, T1 is a 1, Q should toggle from a 0 to a 1, toggle from a 1 to a 0. All of these are toggles. Zeros become 1s, 1s become 0s. And then Q0 plus, well, most of the toggle inputs for T0 are 1, so mostly Q0 is going to get flipped. So Q0 is 0, 1, 0, 1, that's going to become a 1, 0, 1, 0. 0, 1 is going to become a 1, 0, 0 is going to flip to a 1. This last row, T0 is a 0, so Q is not going to change. So that's going to stay as a 0, 1. So now you can put in your final output column, what's the next state, S01, S10, S11, and so on. Does that make sense? So like I say, most people, it looked like they had the right steps, right? They had the right columns in here. Make sure you have the equations down, okay, so that I can follow your work. Be really careful with XORs, and then be careful when you apply the toggles, right? Put down a T flip-flop table if it helps you, and make sure when the T input is 1, your Q flips. When T is 0, your Q does not flip. And I might have mistakes in here. That's not impossible. But you spot checked me, so. All right, so where does this leave us? Present state, input, next state, outputs. That's the essential piece of a state machine that we're after. That's what we use to define a Turing machine in 215. That's what computers are. They're Turing machines. They're just things that say, if this is my present state and this is my input, I'm going to go to this new state and I'm going to generate these outputs. And just do that one after another, and you've got modern computers. All right, so let's make a diagram. Diagram is the last piece. And I didn't already diagram this, so I don't know what the best way is to make the states. So I'm just going to make my state picture the way I usually do. S00, S01, S10, S11. All right, and this is easy because I know I've got 4 states. They're right there in my state table. Okay, let's talk about outputs. So go back to your diagram or your equations if you prefer. So a more output depends only on the state, not on the external inputs. So Z2 is absolutely a more output because it only depends on Y1 bar in particular. So Z2 is going to be a function of the state you're in. Z1, we can see right away, one of the inputs to that AND gate is X. That's an external input. Z1 is a mealy output. Depends on not just the state, but also the input values. So this helps us draw our key. So here's our state. And Z2 is a more output, so we can list it as part of the state. So state Z2. And then a transition arrow, the input is X, and the mealy output is Z1. So that's what these things should look like when we finish drawing them. All right, state S00. Let's put in the more outputs while we're in here anyway. So that's just Z2. So state 0, Z2 should be equal to a 0. Sorry, Z2 is equal to a 1. State 0, 1, Z2 is also equal to a 1. And state 1, 0 or 1, 1, Z2 is always equal to a 0. All right, so state 0, 0, input is an X. 0, 0, input is 0. You're going to go to state 0, 1. So that's a 0. And state 0, 0, input is 0. Your output, Z1, is also a 0. 0, 0, and your input is 1. You go to state 1, 1, and your output is a 0. So 0, 0, we go to 1, 1. And in fact, our output Z1 is almost always 0 except for this last row. Okay, state 0, 1 goes to 1, 0. If your input is 0. And state 0, 1 goes to 1, 0 if it's a 1. State 1, 0 goes to 1, 1 if your input is a 0. State 1, 0 goes to 0, 1 if your input's a 1. So this comes back. State 1, 1 goes to 0, 0 if your input's a 0. So that goes up here. And finally, state 1, 1 goes to 0, 1 if your input's a 1. This is 1, 1 goes to 0, 1 if your input's a 1. And in that case only, your output Z1 is a 1. So there's your output. So there's your state diagram. So even with a little bit of crowding, that's easily 2 pages, right? So these are a lot of work. And you're not going to see like 10 of these on the final exam. You'll see probably 1, maybe 2. Probably 1 that like is a full-on, you know, here's a circuit diagram, do all of this. But then you might see 1 that's like a really simple circuit and you just do some analysis on it. Because they take, I mean, we've been at this for 15, 20 minutes. And I kind of knew how to do it ahead of time, so. All right, so the important thing here is make sure that the process is clear to you, okay? Doing each of the steps and getting them right and getting the 1s and 0s perfect and so on, that's just practice and, you know, good sleep and things like that. But the process itself, right, the what are the steps, why are we doing this? Right, why is this a 1 here and a 0 there and so on? That's what you want to be practicing and talking about and asking about. Yeah? Oh, so Z2, if we look at the equation, it only depends on the state variable, Z1. Or if you look at the circuit diagram, you can see it only depends on the output of the flip-flops. That's what we mean when we say an output is a Moore output. It means it's only a function of the flip-flop values. Whereas Z1 depends on flip-flop values, but it also depends on this external input X. If it depends on an external input, we call it a Mealy output. And so more outputs, since they only depend on state, they can get listed inside each state. But Mealy outputs, since they depend on the state and the input, they have to go on the arrows, because the arrows correspond to the input value. All right, so other questions on that? Okay then, questions on homework, whatever we're up to, homework 7. Yes?
What's between a full encoder design and a one-hot encoder design?
Good question. Okay, so this is this weird little machine with 2 states. 2 states A, B, 2 inputs X, Y, and the information is coded in this table instead of a state diagram. And it asks you to do 2 implementations, one with a full encoded design, one with a one-hot encoded design. Okay, so terminology here. Full encoding means you're basically using combinations of flip-flops to represent states. So we have 2 states here, A and B. So this is how we make our state table. We might have, so how many flip-flops do we need if we want 2 states? You can get away with 1 because a flip-flop has 2 possible values. So we might have 1 flip-flop, Q0, and here's our state. And Q0 is either a 0 or a 1. Well, we might just say state, if Q0 is a 0, that's state A. If it's a 1, that's state B. So this is full encoding. And it's what we've been doing, okay? It's exactly what we've done every time that we've made a state table. We've been using full encoding. One-hot encoding means that at all times exactly 1 flip-flop output is going to be 1. And all the other flip-flop outputs will be 0. You're always guaranteed that exactly 1 flip-flop is outputting a 1. And with one-hot encoding, you use a flip-flop for each state. So here we have 2 states. We would use 2 flip-flops, Q1, Q0. And the values of the states would be as follows. This might be state A, this might be state B. These are considered illegal states. The first state's illegal because you don't have a flip-flop outputting a 1. The last one's illegal because both outputs are 1. Right? The only legal states for a one-hot encoding is exactly 1 flip-flop is a 1. Yeah?
So when you're making this state table, do you have to have those illegal states?
Yeah, I would include those, unless you had, like 8 flip-flops for an 8-state system, and then you'd have, 248 rows of dashes, so you wouldn't list all of those. You'd just list the ones that. Yeah.
Can you put both of them into the same truth table, or do they have to be separate?
Yeah, this is all one truth table. It's just a different state assignment table, right? So now when you're making this thing, right, you're synthesizing it. Your present state is, even though you've only got 2 states, you're going to have 2 flip-flops for it, right? So XA, or 0A, 0B, and so on. But your values for Q1 and Q2 would come from this table instead. But yeah, it's still just going to be one table. And there's going to be combinations of this where you're not going to care, right? So whatever your input is, if Q1 and Q0 are both 0, that's an illegal state. So we can just say we don't care what the new values of the state variables are going to be. We don't care what the outputs are. We don't care what the inputs of the flip-flops are. Bunch of dashes. Dashes should make you happy, right? Because when you have dashes, your K-maps get easier to cover. Your equations are simpler. Your circuit's easier to build. Again, when we have software, there's a checkbox in coding. And you can check full encoding or one-hot encoding, and the software does all this for you. Right? But to write that software, you got to know what this stuff means and to use it efficiently. Other homework questions? All right. So Microsoft took over Minecraft, and among other things, I can't load my old worlds anymore. So I told you a while ago I would show you some logic gate processing in Minecraft, and I can't load my old worlds to do that, but I have a video of a Minecraft walkthrough I made. Actually, I put it on Canvas too. Come on, spell right. Okay, so how many people here play Minecraft? Minecraft is awesome. Minecraft is like programming, okay? You have very simple things that you can do. It's like assembly language programming. You have like 5 things you can do. You can clear a register, you can increment it, you can jump somewhere, you can test to see if something's 0. That's it, right? And you got to build, our modern world with that. Okay, Minecraft, same thing. You've got, your hands, and you can use that to chop down a tree. But once you have a tree chopped down, you can make wooden planks out of that wood, and you can use that to make sticks, and you can make a wooden pickaxe, right? And you can use that to dig stone. You can use a stone to make a stone pickaxe. And you can use that to dig up coal, and you can put that with your sticks and make torches, and now you can go underground and find more stuff. And it's this bootstrapping process, right? And so Minecraft is exploration, it's building things, it's fighting creepers and zombies and skeletons if you like playing non-peaceful. It's problem solving, basically. So one of the features of Minecraft is this mythical ore called redstone. And redstone is kind of like a semiconductor. It lets you do things like what transistors do. And you can find wiki pages that will tell you if you take a little blob of redstone ore and you put it on top of a piece of stone and you put this kind of torch over here, and you put something over there and something here, and you put these switches there, and you flip both of these switches to this one position, the output turns on and this torch lights up, right? And you can build logic gates with this. And if you can build a NAND gate, you know you can build anything, right? If you build a NOR gate, you can go to the moon, right? Build the Apollo guidance computer. And so it's the same thing in here. You can build basic logic gates, but you can take those and put them together and build bigger and bigger things. Apparently, the guy who created Minecraft, which was just kind of like his own little project he did, he pitched it to his game company. They weren't interested. They thought it sounded goofy. And so he did it on himself, right? And he's like one of the richest people on the planet. And apparently, somebody built a working CPU on Minecraft. And the first time he saw it, he said it just like blew his mind. Because he had no idea you could do this. Even though he's the one who came up with this game, it had never occurred to him that you could do something that complex and fantastic as implement an entire CPU, right? And this person did this, and you can find videos for it, and it's a behemoth, right? And it's just built up piece by piece, right? It's the same way that you build your traffic light circuit, one chip at a time, one wire at a time, one hole at a time, but you put it together and you bootstrap your way up to this huge control system. So it's a fun environment. It's not at all addictive, by the way, right? You can play for 2 minutes and walk away. It's never a problem. It doesn't suck up your weekend or anything. So the redstone is interesting to mess with, and people make like combination locks so that other players can't get into their house and steal their stuff. And you can make booby traps that only you can disarm. I saw a 3D printer that somebody made, and you can make a blueprint for something and feed this thing the blueprint, and it'll actually like build in 3D this thing that you described on your blueprint, so you can make more complex machines and so on. So for one of my older 250 classes, I put together some redstone gates and just kind of did a walkthrough of it. And it's a different way to kind of explore some of the concepts we've been working with. We've been doing this mostly on paper. You do it a little bit in the lab, but this is another way. It's more visual. And if you're actually building the stuff, it's more kind of hands-on output. So I don't know where my sound is going to be, but. And this is about 15 minutes, and then we'll take a break after this, but I won't be offended if you leave early. But we'll come back at 1 and lecture. So let me go ahead and play this. Let me see if I can get noise. We got a few minutes. I gotta mess with this. Oh, it's not gonna work for me, man. All right. Well, I'm just gonna crank my speakers and see. You kind of hear that?
Yeah.
So here's an inverter, it's a not and basically switches that you can flip one way or another, and they send a high or a low signal. And I'm mostly using these pistons that go up and down depending on. There's random animals running around. And so if I flip this switch, the piston comes down. If I flip the switch this way, the piston goes up. And I'm indicating on this little sign here. This is the 0 position, this is the 1 position. Yeah, there's no way to see that. 1 down 0, so I'm putting in a 0. So I'm using pistons for output instead of like torches or something. And switches, you just hit and it'll move one way or another.
Flip this to a 1, I've got a signal going down here. This block's basically an inverter.
All right, AND gate, right? Both inputs have to be 1.
1, 0. The output's low, but if both inputs are high, then the output's high. So that's an AND gate. Okay. Keep that in mind. Let's look at something very similar. So this is a NOR gate.
Okay, NOR.
So right now these are in the 1 position, that's to the left, and the piston's supposed to be giving us the NOR, so it's doing A or B inverted. So if either or both of these are 1, the OR will be 1, the output will be 0, and that's what we're seeing right now. If I flip one of these, it's a 1 ORed with 0 is a 1, the NOR is a 0, so the piston is still low. If I flip this one so that both of the inputs are 0, then the piston's high. 0 OR, the 0 will be 0, the NOR will be 1. But if I have one of them high, or both.
Everyone got that as a NOR gate? All right, got a trick coming up.
Make sense so far? Okay.
Do you have all your logic running underground or something?
No, it's all below ground. Well, there's one spot where I have some trenches, but the torches are just in case it's nighttime. Those are regular torches. You can make redstone torches. Those are how you make logic gates. Yeah, so this is a redstone torch. That's how you make a gate. A redstone torch. Yeah, clock you feed. Yeah. All right. So hold your thought on this NOR gate, right? So both inputs are 1. One input's 1, and the output is 0. And both inputs are 0. The output goes high. That's a NOR, right? Okay. Blink for a moment and reimagine what you're seeing here. Suppose this is the 0 position, and this is the 1 position. Just flip this sign around, so 0 is over here, and 1 is over here. So both my inputs are 0, my piston is 0. One input is 0, the output's low. The other input is 0, the output's low. Both inputs are high, the output is high. What is that? That's an AND gate. So what is this? Is it a NOR gate or is it an AND gate?
Okay, that's De Morgan right there.
It depends on what you want it to be. It's De Morgan.
And it's really our point of view.
Right. If we simply change this to be...
Right, so it's doing the same thing. It's the same circuitry.
Inputs are X and
If we
Y,
think those are the 1 position, it's an AND gate. If we think that's the 0 position, it's a NOR gate.
tell us that the non-
It's the same hardware.
Same as the AND of X bar bar with Y bar bar.
That's Boolean gibberish, don't worry about it.
So a NOR gate and an AND gate, they're doing the same thing in some sense. We're interpreting the inputs differently. But based on that interpretation, this one device is either doing an AND or it's doing a NOR. And this is a bit of a hint to why we keep seeing these duals popping up in engineering, in computer science, and math, in the universe.
Pacific
We see these
Northwest.
things that come together, ANDs and ORs, KVL and KCL, and so on. And at some level, I think the reason we always see these things paired together is because they're actually the same thing. Like KVL and KCL are actually the same process of analyzing. ANDs and ORs are in some sense actually the same thing. So that's a little hint to why, for me at least, these duals seem to appear so much. There's usually thunder in the background. I got the sound off. Alright, so what's going on over here? 3 inverters. So this is our favorite.
So this was our start of sequential circuits. 3 inverters with the thirds output feeding the first input.
Again, talking about sequential circuits. The output of this inverter is a 1, which makes the output of this a 0, which makes the output of this a 1. And since you have 1 going in here, the output goes to 0. And it oscillates. Because it's running, it's running on my laptop.
Yeah, this is how you make like mining equipment and stuff like that.
So there's an A-stable circuit, there's 3 inverters with the output coming back in. If you do 1 inverter, it's not enough of a delay to actually get this work. At least I can get this work. 3 inverters does. Same thing in 208. If you actually take 1 inverter and connect its output to its input and look at it on a scope, you don't see it oscillating. But if you connect 3 of them, you will see this oscillation. But you need a certain amount of delay. Alright, so there's a A-stable circuit.
Alright, 2 more circuits.
Here's an SR latch.
Yay.
So there's my reset input, 0 to the left, 1 to the right. There's my set input, 0 to the left, 1 to the right. And there's, where's my output? There's my output. So right now the output is a 0. If I flip this reset line, nothing seems to happen. But if I flip the set line, my output goes high. And when I bring the set line back to 0, the output stays high.
Alright, there's your memory. Remembers what the last switch was.
The reset, it goes low, and when I bring it back to the 0 position, it stays low. So this is the essence of a sequential circuit. My switches are both in the 0 position, and the output is low. Go out for a cup of coffee, come back a few minutes later. The switches are both in the 0 position, but the output is high. So you can't determine the output just from the values of the inputs. You got to know the history. Okay, that's what sequential circuits are all about.
By any chance, is it possible to build some sort of 5x5 timer in here?
Yes.
Oh, there is?
I don't know if anyone's actually implemented a 5x5 style device, because that would get into some analog implementations. But you can certainly mimic the things that you can do with a 5x5, a lot of those, definitely. And I think some people who do it, well, the person who built the ALU, they did it by hand. I think some people have done stuff by using mods where they can tell it what they want the system to do.
If you like Python, you can back end Minecraft really easily and take a lot of the pain out of building large things.
Alright, so that's
But that's half the fun, is like doing it by hand.
It depends on which of these have been asserted most recently. They'll do what the value of the output will be.
So if we have an SR, we can use that to build a D, right? And once we had a D, that was kind of where we took off from. So the last circuit uses an SR and some logic to build a D latch. This is a bigger circuit.
I made a flat world. When you create a Minecraft world, you can tell it to make everything flat. It's basically featureless because I wanted to build these circuits. But normally it's got mountains and trees and rivers and oceans and all kinds of things. And it's much more interesting to kind of explore.
How long did it take you to make this?
I think I spent about an hour. I was procrastinating. It's like a traffic intersection simulator. Should have been doing something else. Alright,
sense?
So that's a D latch. And all of these things are just built from combinations of the other devices. So I built a door gate. I put two of those together cross-coupled to make that SR latch. And then I added this gate push.
You can see some holes in the ground up at the top. So I had to cross two wires. So I had to go underground to do it. All right, so that's just a different view of some of this stuff. And if you play Minecraft, definitely get into some redstone because you can do some really cool stuff with it. All right, so let's take a 5-minute break, and then I want to do one more show and tell for you. I want to show you what goes on inside a very real computer system. I want to show you some diagrams that relate some of the stuff we've done to how computers actually work. And then let's start talking about Verilog for most of the second half. Let's take about 5 minutes, come back about 1 o'clock, and we'll go from there.